Electrochemical cells. An electrochemical cell uses the electron transfer which occurs during a redox reaction to produce electrical energy. So we've been thinking about redox reactions and trying to remind ourselves about what happens, and that something gets oxidized, loses electrons, whilst some other species is reduced, gains electrons. If we can capture that transfer, we can use that electrical energy, that movement, that flow of electrons as a source of electrical energy to power our devices. So for example, an electrochemical cell is just a battery. It would be maybe in your mobile phone, maybe in your calculator batteries. So let's just have a look at this reaction between copper sulfate and zinc, and it says in terms of electron transfer, describe what is happening in this reaction. So if we look at the zinc first, the zinc is going up in oxidation state. It is losing 2 electrons, so Zn is losing 2 electrons, going from Zn to zinc 2 plus. Zn is oxidized. And then if we were to look at the copper starts as +2 in copper sulfate and ends at 0. Cu2 plus is gaining 2 electrons. So we can say that Cu2 plus is reduced. So something is being oxidized and something is being reduced, and we've written 2 half equations to show those two processes separately. So if we remember, a redox reaction is composed of 2 half equations. One for oxidation, the zinc, and then one for reduction. We can start to look at this next bit, the electrochemical cell, and say that it must consist of 2 half cells. So a redox reaction has 2 half equations. An electrochemical cell has 2 half cells. Again, one for oxidation, one for reduction. So we've got a redox reaction made of 2 half equations and a cell made of 2 half cells, and they match up. So what is a half cell? Well, it shows us the 2 species, the before and the after, the reduced and the oxidized species of the same element. So the copper half cell is going to have, from this copper half equation, some copper 2 plus and some copper. It's the 2 species in their different oxidation states. So let's just highlight same element in different oxidation states. When we look at the copper half cell, we're going to see that we've got copper 2 plus, and that's the solution, gaining electrons. I'm going to draw this reversible. This is because when you are picking half cells from a table, they will all be written as reductions like this, but sometimes they won't go in this direction. So we write reversible. It's because we're going to choose later which direction we're going to draw our equation in. So a half cell is simply a beaker, and in that beaker we need to put these 2 things. So we've got something aqueous, that's our solution, and the standard concentration is 1 mole per decimeter cubed. So we need 1 mole per decimeter cubed of the copper 2 plus ions. So e.g., that could be a solution that was like 1 mole per decimeter cubed copper sulfate, for example. We then need to have copper solid, and we're going to use a piece of metal as an electrode. We're going to connect it to a wire so that we can connect it outside of our half cell later on. And this is our copper metal. So we have the 2 species that are present in the half equation. So we've got the copper 2 plus in the beaker as the solution and the copper metal as an electrode. Then it wants us to do the zinc half cell. Now, like I briefly mentioned, we always write half equations for half cells as reductions until we know which one ends up being the oxidation. So I am going to reverse this from what was written above to be a reduction, but with the reversible arrow so that it can change its direction if we want it to. So again, we're going to draw a beaker. We're going to have the two species, so Zn2 plus AQ at standard concentration 1 mole per decimetre cubed. So e.g. some solution that contains that. Quite often I pick nitrates because nitrates, the nitrate ion doesn't react with anything else that might be present in our cell later on when we connect it all up. And so it's useful to use a nitrate. And then we're going to have our piece of zinc metal. So we can see at the bottom it says the convention for writing half equations for electrode reactions is to give them where the forward reaction is a reduction. We've given both of these as a reduction. So if we just take a step back a minute, we said we've got a redox reaction made of two half equations, and each of those half equations represents half of the cell that we're trying to build. And so we have these two half cells, one for each half equation, and my half cell contains both species present in the half equation in their standard conditions. So we've got a copper electrode in a copper 2 plus solution and a zinc electrode in a zinc 2 plus solution. So now we need to connect it, because if we want to get the electrical energy out, we need to connect them. We're going to connect them two ways. We're going to have an external circuit, and this is all about our external circuit. And then we're going to have a salt bridge connecting our solution. So an external circuit is going to connect those two wires that were coming out of our electrodes, and our salt bridge is going to connect our two solutions, our copper 2 plus and our zinc 2 plus, and different charge carriers will be used to carry the current through those different sections. So we're going to connect our two beakers with an external circuit, and that is usually just a wire. And because wires are made of metal and metals conduct because they have delocalized electrons, then electrons flow through the wire. Then we're going to connect our two solutions, our copper 2 plus and our zinc 2 plus, with what's called a salt bridge. A salt bridge is a piece of filter paper, and it's soaked in either potassium nitrate or potassium chloride solution. You often have to label that in the exam, so that's why they're in bold. But because they're ionic, free ions flow through the salt bridge. The ions in the salt bridge mustn't react with any of the ions in the half cells. So what that looks like in reality is sometimes if we use KCl, it can't always be used. It can't be used for the Ag plus half cell, that's a silver half cell, as Cl minus reacts. We know that we get a white precipitate with Ag plus. KNO3, potassium nitrate, is the best choice as nitrate ions are unlikely to react. The electrodes are then connected with a high resistance voltmeter. If you remember it from GCSE physics, that's just a V in a circle like this. And that's going to register the EMF in volts, and that is what we're going to call the cell potential, the potential for it to generate current. So the cell is set up under standard conditions, and we know the standard conditions in chemistry are 100 kilopascals, 298 Kelvin, and 1 mole per decimetre cubed. So let's put all that together and create the copper zinc cell from our two half cells. So when we connect this cell, the copper electrode ends is connected to the positive terminal of the voltmeter. And what we mean by that is when you connect the voltmeter to these two beakers, if your voltmeter reads negative, well then you've got your voltmeter in back to front. So you reverse it, and then when you get a positive reading on the voltmeter, you'll be able to look and see which terminal of the voltmeter the copper electrode is connected to. And whichever thing is connected to the positive terminal of the voltmeter is the positive electrode. And so copper is the positive electrode. The IUPAC convention for these diagrams is always to put the positive electrode on the right-hand side, except for this strange situation where you're trying to find the values by measuring them against the primary standard of hydrogen, which is where you always put hydrogen on the left, but we will come back to that in another video. So positive electrode on the right-hand side is the convention for any two cells that don't include hydrogen. And so we were saying that the copper is our positive half cell. So we're going to put the copper on this side. So remember those two half cells had these two half equations, always written as reduction. Okay, so these two half equations, and we connected them. So if we go back and think about what we drew earlier on, we had a piece of copper solid in a solution that contains one mole per decimeter cubed Cu2+. So if we're asked to give an example, we'd have to actually pick a chemical, not just write Cu2+. So e.g. 1 mole per decimeter cubed copper sulfate. Okay, that's AQ. And a piece of copper metal. Then on the other side, on the left-hand side, we've got the negative. Remember, that was a piece of zinc solid, and that was a solution containing 1 mole per decimeter cubed Zn2+. E.g. 1 mole per decimeter cubed zinc nitrate solution. We're connecting those two via this external wire and a high resistance voltmeter. And we connect the two solutions via a salt bridge, which contains KNO3 solution. So this is our diagram of our cell. It says write an equation for the reaction occurring at the negative electrode. So the negative electrode is the left-hand side, and at the left-hand side we get oxidation. So we got the negative electrode, and the negative electrode is always the oxidation. And remember, it was about zinc, so we look at our equation and it can go either way, but we need it to be an oxidation. So we go from zinc, and now we use a one-directional arrow because we're choosing that it's an oxidation. And then at the positive electrode, we are going to get reduction. And our positive electrode was our right-hand side, reduction at the right-hand side. And that is our copper 2 plus 2 electrons goes to copper. So we had a look to see which of our beakers was connected to the positive electrode of the voltmeter. Positive terminal of the voltmeter, sorry, and we say that's the positive electrode, we draw it on the right hand side and we do its equation as a reduction. So this is the positive electrode and this is the negative. Electrons are always attracted to the positive electrode, so they flow from the negative to the positive. So electrons leave the surface of the metal, delocalized electrons leave the surface of the metal, they travel up the wire through push against the high resistance voltmeter, and those of you who do physics will know that very few electrons actually pass through a high resistance voltmeter. So they push against it. On the other side, electrons are being pulled from the wire, from the direction of the voltmeter down towards the copper, where they go to the surface of the copper metal, and the Cu2 plus is able to use them from the solution and pick it up and deposit onto the electrode. When you read the voltmeter for this reads 1.1 volts. So we've got a star box there, oxidation, and we can link it to what we highlighted. Oxidation occurs at the negative, and our reduction occurs at the positive. So the negative is the left-hand side, the reduction is the right-hand side, reduction on the right. And then electrons flow from our negative to our positive so that they can be gained for reduction. Okay, so there's just the last little bit to do with setting up a cell, and then we'll delve into them in another video. So we've got on the left-hand side, if we go back on the left-hand side, we've got zinc losing electrons. They're going up the wire and they are pushing against the voltmeter. On the right-hand side, we've got copper 2 plus gaining electrons, pulling them from the wire, pulling against the other side of the voltmeter. How much of the 1.1 volts was to do with zinc's ability to lose, and how much of the 1.1 volts is to do with copper's ability to gain? So we've got this potential difference, this difference of 1.10 volts. How much of that is to do with zinc and how much of that is to do with copper? What we do to find that out is measure something called a standard electrode potential. We decide on a zero line, a zero mark between these two, or it could be to the left or to the right of these two. Actually, for this one, it does fall between them. We decide on something that has zero potential, and that is just by definition a zero. We kind of made it up. We've just decided, like with temperature, what we just decided that water freezing was 0 degrees C, and then we made a scale based on that. We've just decided that our standard hydrogen electrode is the zero value. How much of this difference is to do with copper's ability to pull electrons, and how much of it is to do with zinc's ability to push them? And when you actually measure their standard electrode potential against hydrogen, you find that hydrogen is around about here. This is the zero. In fact, I'll put the zero at the bottom. This is the hydrogen. So H plus H2. This is the zero. What we find is that copper is 0.34 volts more likely to attract electrons than hydrogen, and zinc is minus 0.76. And the difference between copper and zinc, if you do that on your calculator, is 1.1 volts. So how much of it is to do with copper and how much of it is to do with zinc? We'd find that out by measuring against hydrogen as standard. Okay, so we can't measure one half cell on its own, so we have to make a primary standard, and we call that primary standard the standard hydrogen electrode. And by definition, if you're asked why the voltage is 0.00 volts, it's because we just decided it is. By definition, it's 0.00 volts. So that's the answer. Why is it 0? Because by definition it is. So what does the standard hydrogen electrode look like? Well, if I show you the equation for reduction of hydrogen ions to hydrogen, this is the two species in different oxidation states, we can see that we need these two species in our equation. So one of them is AQ, so why don't we label our solution, this little arrow here, I'll make it a bit bigger, 1 mole per decimeter cubed H plus AQ. We haven't actually got, hydrogen's not a metal, so this little piece of metal here can't be hydrogen, and so we're going to use something that isn't going to react but will allow electrons to transfer. I'm just going to move this up a tiny bit so that I've got a bit more room, and just correct my arrow. Okay, so this is actually, we're going to use platinum because that's an unreactive metal. We need to put the hydrogen gas in somewhere, so somehow we've got to bubble the hydrogen gas in, and that's what this funny little chimney is about. It allows us to force hydrogen gas in at the standard condition for a gas, which is 100 kilopascals. So what have we got in here? We've got 100 kilopascals H2 gas. We've got a temperature of 298 Kelvin. We've got a platinum electrode, which is inert, but conducts electrons into the circuit, into the external circuit. And then we've got 1 mole per decimeter cubed H plus ions. So that could be e.g. 1 mole per decimeter cubed nitric acid or hydrochloric acid, or if I wanted it to be sulfuric, I'd have to have 0.5 moles per decimeter cubed sulfuric, because that gives me 2 H's for every sulfuric, so I only need half as many moles per decimeter cubed of sulfuric acid to get the 1 mole per decimeter cubed of H plus. And that's the thing we connect on the left hand side to measure any of these values. So we would, with this copper zinc, we would have put hydrogen on the left and we would have put copper on the right, and copper is more positive, so it became the positive electrode, and the voltmeter read plus 0.34. When we want to measure these standard values so that we know relative to hydrogen where they are, we always put hydrogen on the left, and when we would have measured zinc, zinc would have been attached to the positive electrode, but the voltmeter would have read minus 0.76, so that would have been a bit strange, but what's it telling us is it's less likely than hydrogen to gain electrons, and we can see the difference between copper and zinc then is 1.1. So I'm going to spend a lot more time in other videos looking at how we can use this information.